Okay, good afternoon. Great to see so many people in person in the same room. Excellent. Thanks for being with us here at EPFL and with us online. It's my great pleasure to welcome today Professor Paolo Ricci, who is Associate Professor at the Swiss Plasma Center, Dr. Alessandro, who is Research Scientist at the Swiss Plasma Center. Their talk today is entitled, Can Artificial Intelligence and Machine Learning Help Us to Light Up an Earthbound Star? Before we dive into the presentation, which roughly goes 40 to 45 minutes, just some reminders. If you have questions, use the chat. If you feel it's urgent, the speakers kindly agreed to take your questions in line. Otherwise, we have 15 minutes roughly at the end to take them up and discuss them. Now, without further ado, Paolo, Alessandro, floor is all yours.
Hey, thank you, Jan, for organizing all this. It's a real pleasure to be here and to have the opportunity to tell you a bit about what we are doing at the Swiss Plasma Center. So the talk is structured in the following way. First, I will talk a bit about the crazy idea we have at the Swiss Plasma Center, that is to light up an earthbound star, and some of the challenges that you can imagine are associated to it. And then I will hand you over to Alessandro, that will talk you about, he's actually our expert in artificial intelligence and machine learning, and we'll go a bit more into the details of what we are doing this week. So let's start. So what we want to do is to use the fusion reaction, the same one that takes place in the sun and in all stars, to produce electricity. The reaction that we want to use is the one between deuterium and tritium. When they interact, they fuse together, they release a huge amount of energy. Just to have a comparison, is about 1 million times the energy that is released in a combustion reaction. And well, this energy actually goes into the kinetic energy of the product of this reaction, the helium and the neutron. Now, the helium can be used to heat the fresh fuel, deuterium and tritium, that comes into the machine, keep interaction going, while the neutron energy can be used first to produce electricity, and then by having the neutron collide with lithium, we can produce tritium that, in contrast to deuterium, cannot be found in nature. So, as you can see, this is an ideal reaction to produce energy. There is no production of greenhouse gases, no CO2. It's the primary fuel elements are the deuterium and tritium, and these are fairly abundant elements on our planet. It does not depend on the season, on the time of the day, does not depend on anything that may affect the other sources of energy, and it's safe. There is no chain reaction. If one wants to turn off the process, it's just enough to close the valves, injecting deuterium and tritium, and this is it. Okay, this is all nice, but of course comes to a cost. And the fact is that it's very difficult. It's very difficult to have such a reaction. You need the temperature that are of the order of 100 or larger, 100 million degrees, is about 10 times the temperature in the core of the sun. And well, what happens at this temperature? Matter at this temperature is fully ionized. It means that the electrons are stripped away from the atoms. The matter is therefore a sort of gas, let's call it this way, of electrically charged particles, ions and electrons, that we call plasma. Now, this electrically charged particle can be confined by using a magnetic field. Why is that? Well, when you have a magnetic field, I am drawing it here, an electrically charged particle, because of the Lorentz force, is constrained to move along it. So magnetic field can actually provide some confinement. And this is what we are trying to do. So how do we want to make fusion? We build by using a complex set of magnets, magnetic cage, such as the one that I am representing here. It's a donut-shaped cage. Then we put the mixture of the deuterium and tritium there. We heat up to get the plasma state. And at that point, we expect fusion reaction to take place so that we can extract our the energy we need. Now, what are the devices where this is done? Well, we use Tokamak devices. We have actually one here on campus. It's TCV at the Swiss Plasma Center. Is actually the largest experiment that we have at EPFL. If you want, we always invite, and the visits of this facility, I think, is honestly pretty impressive. We are very happy to organize visits and show you this experiment, so do not hesitate to ask. Now, this is a device that is TCV that is mostly used to study the impact of this magnetic cage on the plasma dynamics. The largest experiment that nowadays exists is JET. It's a European experiment that is located actually in England near Oxford. And maybe you have followed the news. It was towards the end of last year. There was a discharge, a record discharge. The one that I am showing here in this movie was a 5-second discharge, where actually the world record of fusion energy was produced 59 megajoules. Now, this it was the record energy that was produced, but actually we injected more energy than what we got out. So we really want to produce energy, and this is what ITER will show. Now it's the next experiment. You can see how we are scaling up of the dimension. This is the TCV Tokamak, this is the JET Tokamak, and this is how ITER will look like in comparison. And here you can see the machine, compare it with the size of a man. Here it's a collaboration between 7 international partners, and the goal is to show that actually one can produce energy from fusion, and will be sort of the step before the demonstration fusion reactor. In ITER, in fact, we will have heating. We will heat up our plasma with about 50 megawatts, and we expect to get about 10 times more energy, 500 megawatts from it. ITER is being constructed actually not far away from here. It's in southern France, near Aix-en-Provence. Cadarache is the name of the town. And here is a movie that shows it's a few months ago now. Workers move forward even more. What's the status of this project? What you can see is actually the land where ITER is being built. The big building is actually the assembly hall. Other buildings that you can see are necessary because some components cannot be transported to the ITER site. They are too big, so they have to be produced right on the spot. Now, about 85% of the infrastructures are completed. So we are approaching quite quickly the phase, the first plasma. Now we will enter inside the assembly hall. This is where the ITER is being constructed. Okay, as you can imagine, it's a huge workshop. This is a piece of the vacuum vessel. It's divided into 9 sectors that will be welded together. Here are some of it, and actually will host the plasma where the fusion reaction will take place. All these pieces will be put in the Tokamak pit. Now we will see just beyond that wall. We will see it in a second, and it's basically, yes, now we are getting there, where the ITER is being constructed. And actually, one of these parts has been already put in this hall, and in a few years, we hope to see the first plasma. Yeah, just a few numbers here is where the Tokamak will be located. So just a few numbers about ITER. So in order to have the field, a magnetic field necessary, we need to use superconducting cables. There will be 100,000 kilometers of superconducting cables. Actually, the worldwide production has to be significantly of superconducting cables have to be significantly improved. It's about 60 meters high, like the Arc de Triomphe. It counts around 10 million components. The area that you have seen corresponds to the one of 60 football fields. Each magnet weighs, and there are many of them, weighs like an airplane, a 747 at takeoff. The total weight is equivalent to the total weight of the Empire State Building. There are magnets and there are currents, so there are forces associated to them. And actually the forces are about twice as strong as the shuttle thrust at liftoff. And the energy in the magnet is equivalent to the kinetic energy of TGV. And well, maybe what is most impressive is that in these almost 1,000 square cubic meters of plasma volume, there is only 1 gram of fuel. So I think you start to get an idea that this is not easy. So let's see what are some of the challenges associated to what we are trying to do. ITER will allow us to access physics regime that are not explored up to now. For instance, while current machine basically work receiving input heating from external tools like antennas or other mechanisms, for the first time here we will have a burning plasma that is a plasma that is self-consistently heat up by this particle I was mentioning, this helium particle, alpha particle, energetic that are emitted by the fusion reaction. And as you can imagine, a self-consistent heating sort of challenges the control. There are catastrophic losses of confinement that occur, where basically the plasma goes somewhere in a way that cannot be controlled. And these have to be absolutely avoided. Here is a movie of one of these, what happens. Basically, everything now is not very clear, but everything is going well, and then bam, all of a sudden you lose the control of the plasma. And these have to be absolutely avoided in ITER because already in JET, which is much smaller, works at much lower energy, it can cause real damage to the wall structure. But even if we are able to control the overall confinement and avoid this global disruption, there are harmful instability that can grow and may be an issue. In fact, you should imagine that in a few centimeters, you go down from temperature that are about 10 times as high as the core, as in the core of the sun, to the room temperature of the wall. This is at the steepest possible gradient, I think you can think in the universe. And if you look at this movie, you will see actually that there are oscillations. It's not constant. There are sort of bursts, intermittent events. And although you may not lose the total plasma, these intermittent events should be avoided or mitigated. If you want a comparison, imagine of what's going on. Basically, you are heating up. It's like piling up sand on top of small mountains. And then when the gradients steepen up, all of a sudden you sort of have an avalanche. And here is a bit what happens. So there are these avalanches of plasma heat that have to be controlled. And in ITER, it becomes a big issue. So we need the reliable predictions. We need the reliable predictions. Why? First, now the design of ITER is fixed, but we want to optimize its safe operation. And then we want to identify what is the demo optimal design. How can we approach that? Well, I think one could imagine that first principle simulation, it's a tool. And there was a large progress on this. Here is the result of one of the simulation we do at the Swiss Plasma Center. Basically, we are simulating the entire volume of TCV, and you can see at the plasma pressure that sort of evolves in this geometry. This is a geometry actually of interest for them, more complicated than the one for ITER. But the simulation of this kind are extremely complicated. And while TCV can be sort of simulated, we are very far away from, with some condition, we are still very far away from simulating ITER or even more demo. The cost of a simulation like this one is 10 million CPU hours, extremely expensive, extremely expensive. Why is that? Well, we are dealing here with a system that is multi-scale. We have to bridge time scales that are of the order of 10 to the minus 10 seconds and sub-millimeter to the machine size, all in one simulation. We are dealing with a multi-physics problem. We have plasma, but we have also neutral atoms that are there. We have impurities from the wall. We have energetic particles that are emitted by this fusion reaction. We have radiation. We have the interaction of the plasma with the solid wall. And the plasma is an intrinsically complex nonlinear medium because it's made of electric charge that respond to the magnetic field that they themselves produce. And all these results into a turbulent dynamics that is actually more complex than turbulence in standard fluids. Because, for instance, there is the interplay with the magnetic field, and also which result in an extreme anisotropy of turbulence, and all this has to be simulated in a complex geometry. So all tools that can help us to bridge from current experiment and allow us to make prediction for ITER and improve our understanding is welcome. And let's see for this, what is the possible contribution of artificial intelligence and machine learning. Okay, thank you, Alessandro.
Thanks, Paolo. Hello, everyone. So now we are going to talk about the potential contribution of artificial intelligence and machine learning in trying to advance the fusion. So as Paolo told you in the first part of the talk, so fusion is one of our best hopes for dealing with different problems like global energy consumption, climate changes, but as every hope comes with a price. And this price is related to the complexity of the system. And this complexity is at the various levels, as Paolo explained us, and also in the data that we acquired during the experiments in fusion. Particularly, we have a massive amount of data that are acquired by high bandwidth diagnostics. And for example, ITER is foreseen to produce like 2 petabytes of data per day, which is quite impressive. These data are highly heterogeneous, so they come with different formats. And even if there are some standards, data ecosystem in general are or can be facility dependent. And they are characterized by a really high dimensionality. We have many diagnostic systems measuring different plasma quantities and properties. And then, as Paolo mentioned, we are dealing with a multi-scale and multi-physics problem. And usually numerical codes need to integrate all these aspects in what we call integrated Tokamak modeling. So here you can see in this sketch some of the, let's say, the main fields where people in the recent years have tried to advance fusion by leveraging machine learning and artificial intelligence. So we start with model reduction that has to do with the attempt of reducing the complexity of the models by using, for example, surrogate models, which are faster to compute the same physics aspects. Then we have the field of real-time control that has to do basically with plasma state monitoring and control, not just in standard situations where the main challenge is to process a high volume of data that is produced by high bandwidth diagnostics, but also we might want to predict some transient events that are occurring during the plasma discharges and to react to them with the plasma control system, or to predict and or avoid disruptions. This is what goes in the field of data enhanced prediction. And then we have boosted diagnostic. So we would like to optimize as much as possible the amount of information that we can extract from the data. And finally, we would like to exploit machine learning and artificial intelligence to try to have a more efficient way to investigate and explore our large and high-dimensional data sets, and in also to understand, for example, in which direction we should move to design new experiments, because as you might guess, experiments are really, really costly. So as we said, the plasma physics is characterized by multi-scale, is a strongly non-linear problem, and we need high fidelity codes, as Paolo mentioned, to be able to simulate some of the physics aspects of the underlying physics characterizing our plasmas. And these codes normally are quite computational demanding. Here in this example, we have 1 second of a discharge. This is the jet Tokamak that is simulated through this code to study microturbulences in the plasma, and it takes something like 1 year on 1,000 cores. So as you might guess, this is not very practical for most of the applications. And so people in this case try to rely on reduced order models, where we try to reduce as much as possible the computational complexity, relaxing some of the constraints. For example, instead of non-linear codes, we use quasi-linear approximation, or we try to linearize the systems. And we can go quite down with the computations. For example, here we are already at 1 day on 24 cores. And if we want to go further down in the model hierarchy, we can rely, for example, on surrogate models based on neural networks. And in this case, we get almost to the compatibility with real-time control. So what we call near real-time application. So with reduced order models, we can speed up the computations, but also we can populate extensive data sets to train machine learning models that are then validated with the high fidelity models. And we can use these data-driven models to replace multi-physics models. And we put all of this together, so numerical codes and surrogate models to try to simulate some of the physics aspects characterizing our plasmas in a workflow that we call integrated Tokamak discharge modeling. So now let's see some applications where we use AI and machine learning to deal with these challenges. Here, for example, the goal of this application is to support the design of the experiments in predicting the evolution of some of the K quantities that are the outcomes of the experiment. So the scientists normally before the experiment would like to simulate how those physics quantities are going to evolve. When we have in input a particular configuration or some settings, like the voltages applied to the coils, the heating power, plasma fueling to get a certain density. And so, and to do this in this particular application, we have relied on this architecture, on this deep learning model that is based on stacked bidirectional LSTM architecture, where the model has access in particular to the widest possible contextual information due to the fact that the information is flowing forward and backward. And at each time step, the model has also the knowledge about the future. So as you might guess, we cannot use this in online settings. This particular application was dealing with the data of the East Tokamak. So East is a tokamak in China, the largest tokamak in China. And here you can see the cross-section of the tokamak and the plasma together with the colloidal field coils to control the shape of the plasma. And among the challenges that we had to face for this application, so first of all, the large amount of data. So for training, validating, and testing the model, this was done over more than 26,000 discharges for more than 500 gigabytes of data. And then since here you can see some of the results for the quick K quantities that I was mentioning before. So the job of the model is to try to predict the evolution of these quantities given the input parameters, and we have to do with multi-scale phenomena. So the model has a really hard job in modeling the evolution of these parameters. But with this particular architecture, so with exploiting this bidirectional flow of the information, the reconstruction, the prediction that you can see here in red compared to the experimental quantities is quite good. And this was assessed with this similarity indicator. But still, there is some issue for, in particular, for the time varying phases. The model is doing a pretty good job in the stationary phases, but it's still missing some feature in this time varying phases. And also is not very efficient from the training point of view. It took really a lot of time to train on this data set. So in order to tackle these challenges in a different application this time, but we decide to rely on a different architecture. Here in particular, the task is forecasting. So we are doing a one-step ahead prediction of the magnetic field evolution in time. And in particular, we are reconstructing this last closed flux surface. That is the outermost closed flux surface characterizing the magnetic configuration. So here I should remove a second the laser point to start this. Okay, good. So here you can see the evolution of the last closed flux surface. You have in red the prediction from the model, and in blue the target. That is a reconstruction with a magnetic equilibrium code. And in particular, in this application, we were relying on one of the most innovative models in deep learning. That is the transformer architecture. So, and as you know, this architecture has brought a lot of attention and interest in the machine learning computing because due to its excellent performance in various tasks like computer vision, natural language processing, and outperforming state-of-the-art models. And here you can see a sketch. So in our case, we are using a variant, of course, that is suitable for time series processing. That is a shifted window transformer, where this was developed initially for a computer vision task. who developed this architecture wanted to deal with the problem of the large variation in scales in visual entities. So if you think to the macrostructures in the images and the videos, going down to the low-level representation that is done with the pixel. And here there is a parallel with the multi-scale phenomena that we can have in time series. So we try to model sequences that have large variation in the time scales. And this architecture was quite efficient for this task, much more efficient than the previous one in terms of training, because in this case, you don't have to process the information in a sequential way. But it allows for high parallelization, so differently from standard recurrent architectures. And also, it's more efficient in dealing with long sequences. You have to imagine that in EAST, we can have a length of the discharge that is 1,000 seconds, up to 1,000 seconds. And we are working with data whose sampling frequency is 1 kilohertz. So we have to deal with very, very low sequences and with multi-scale phenomena and interaction during the evolution of the discharge. And also, it's much more efficient because of, as we know, for the multi-head attention mechanism that is implemented in this particular architecture, that is allowing the model to capture a much richer representation of the interactions and the dynamics in the sequential data. So another field, another application is for control augmentation in modern plasma control systems. In this case, we are dealing with plasma state monitoring and forecasting, as well as with the detection of events, of normal events, very often which we have to react to during the operations, activating specific control tasks. Here you can see a sketch of the plasma control system that is a Tokamak agnostic layer, because it's not depending on the Tokamak subsystems, as you see here, actuators and diagnostics. And in this case, the task and the main challenges for time series processing are related to anomaly detection and classification. Here, in particular in our machine and in our plasma control system, we have deployed some models based on deep learning architectures. One of these is for detecting, is giving us the probability of the plasma of being in one of these so-called confinement states. So now, without going into many details, it's very important to know post-processing, but also during the discharge in which confinement state the plasma is evolving. And in particular, it's important to detect the transitions between these different confinement states. And these transitions are happening on very time scales, whereas other characteristic mechanisms are happening on much longer time scales. So also in this case, the hard job of these models is to try to catch short and long-term dependencies in the sequence data. And one thing that we do also in our plasma control system is to try to merge together these machine learning-based approaches with physics-based scaling laws, model-based approaches, and we try to use all the potential tools that we have to try to detect as accurate as possible for example, these transitions in the confinement state. And regarding event detection, so the extreme side of normal events are disruptions, as Paolo already mentioned. When we have a disruption, basically we are losing the thermal and the magnetic confinement of our plasmas in the time span of a few milliseconds to tens to milliseconds, depending on the size of the machine. And they can potentially damage the machine. So they represent one of the most serious concerns for the exploitation of tokamak as base for future fusion plants. So they are characterized by a really complex physics picture. We have many causes, many different chain of events that can lead to different type of disruptions. Here you can see some of them. As Paolo mentioned, we might have impurities in our plasma, and when the impurities cool down in some regions, the plasma, we have problems because of the strong radiation. We can lose the vertical control of our plasmas that are inherently stable with respect to vertical displacement. We can have the onset of these magneto-hydrodynamic instabilities. So with modes that are rotating with the plasma or not with respect to the plasma frame, and we call them locked modes. So this sounds extremely complicated, and it actually is very, very complicated, but I'm starting to see some worry phase. We are not going into the details of the physical disruption. It will be really complicated, and it will take a lot of time. All I wanted to tell you is that we have a wide plethora of physical causes, technical causes, that are in some cases even unpredictable when we are dealing with failures of some systems. And but independently on the physics, what we are interested in is that when there is a disruption, it's because we are losing the control of our plasma. And this can potentially damage the machine. I think this is a reason good, more than enough to try to exploit any possible tool, including machine learning, to try to predict and to avoid them in the first place, or when this is not possible, to try to mitigate their consequences. So we have done a huge step forward in the understanding of disruption physics, but as for many other aspects of plasma physics, we don't have an omnicomprehensive description with first principle models. And we have to deal with a lot of problems, because as I showed you before, we can have many different paths that are leading to disruption. So this is one of the reasons why historically and traditionally there has been a lot of applications dealing in machine learning, dealing with disruption prediction, and but we have still a lot of issues and a lot of challenges to face. So first of all, what we call the aging of the predictors. What do we mean with aging? So this refers to the hard time that the models have in trying to keeping up with the changes in the operational domain. As the target plasmas and the operation evolve, because there is a learning curve also in this when you operate a machine. And also, in particular, with the generalization of the models. Because already within the same experiment, it's really hard to keep track of all the various dynamics and disruption types. But in particular, it's really challenging when we try to move to different devices. When we try to extrapolate, for example, a model that has been trained on a specific device on another device. This is really, really complicated, and it's not working really well up to now because of many reasons. We have different devices, have different geometries, different materials, so potentially different causes of disruption, but also the experimental program might be different. So we are trying to extrapolate to something that maybe in one machine has never happened. So this is really complicated. And on top of this, there is also the multi-scale problem. Paolo already told us about this. Here you see a sketch where we have the range of variation in time and space. So that it's really a large range of variation. And people try to approach the prediction of disruptions with very different approaches in machine learning, with shallow models like random forest, with deep learning models, trying to exploit also in this case, trying to catch with convolutional layers or recurrent architectures, long-term dependencies in the time series that normally are lost with standard architectures. Here we can see, for example, an application where it has been used a temporal convolutional network using relying on causal convolutions and dilated filters to try to increase as much as possible the receptive field. So at the same time to try to catch multi-scale phenomena, because we can have precursors preceding the disruption that are happening on very different time scales. And as you know, this is a problem for time series processing and for machine learning models dealing with time series. Another problem that that is not negligible is that many of these models are really not transparent. It's really difficult to interpret them, and very often they give as output a calibrated probability from 0 to 1 that there is going to be an impending disruption at some point in time, but we don't know why. And if we want to react, we want to try to avoid the disruption, we need to understand what is going on. What is the cause, the potential cause? What is the chain of events that can potentially disrupt our plasmas? Because we need to react, in principle, we might be reacting in a completely different way with our control system. There is not a unique solution for this. So there are also other approaches that have been explored, going more towards model transparency and interpretability. And in this case, we are in the domain of advanced feature engineering and generative models. Basically, with feature engineering, we try to engineer features that are directly connected to some physics mechanism. And with generative models, here, for example, you have this generative topographic map. You can visualize trajectories. So you can track the evolution in time of the operating point during the evolution of the discharge, and you can encode in this latent space patterns that are corresponding to different types of disruption. You can cluster plasma regimes and try to unveil the boundaries separating, for example, a safe operational space with respect to a space that is characterized by a high probability of disruption. And also, you can have a connection with the engineered features that are physics-based. So, for example, you can investigate the structure of these manifolds, of this latent space with respect to the input distribution of these engineered features. And you can find nice correlations and try to understand what are the most common patterns leading to disruption. And finally, I would like to conclude this overview with the results of this impressive collaboration of the Swiss Plasma Center with DeepMind, that is about magnetic control by deep reinforcement learning, that was already presented a few time ago, also here at EPFL. So here, basically, differently from supervised and supervised learning, we are dealing with reinforcement learning. That is about learning by trial and error, as a human being will do, how to act on an environment to maximize a reward. So basically, if we look at this sketch here, we have what we call an agent that is interacting through specific actions with an environment. And then with respect to the observations that is receiving back from the environment, is trying to learn a control policy to try to maximize a reward. The reward is connected to a particular task that the model is trying to accomplish. That is, in this case, is the control of the magnetic configuration of our plasmas, where the controller, based on deep reinforcement learning, was trying to sustain as long as possible in a stable way these exotic magnetic configurations that are of interest because of various reasons. And it was really successful in doing this. So to conclude, I just want to mention some of the collaborations that we have as a Swiss Plasma Center as far as AI and machine learning is concerned. We have collaborations within the EPFL. We have a project related to a grant with the Swiss Data Science Center. on disruption prediction. We have several links with various courses on machine learning, computer vision here at EPFL, where we grant semester projects, internship, and master thesis to the students. Then we have various collaborations at different levels. We are part of Fusion and different international programs in Fusion to develop the physics basis and the technological know-how for future fusion reactors, like ITER, as Paolo mentioned, Spark, Demo. And then we have also coordinated research projects with the International Atomic Energy Agency on the use of artificial intelligence to accelerate fusion research. And so the conclusions. We have seen a lot of applications. The main challenges try to exploit machine learning and AI for advanced different fields in fusion, but still there are a lot of challenges that are related. So here I try to summarize in few bullet points, but there are many of them. In particular, physics understanding. Physics understanding requires model transparency and interpretability, which is not a negligible aspect because ITER, for example, will still be an experiment. So we want to understand what is going on. We don't want black box, completely black box approaches. And also the extrapolation from current machines, the experiments in the current devices to next step devices is quite challenging using this kind of techniques. And we discussed why. And also another point that is not negligible is how to qualify the performance of AI and machine learning based systems. Every time we are dealing with something that is connected to a critical application, to the safety of the machine, how do we qualify these systems? This is something not trivial. And this was the conclusion. I hope to not be too long. Okay.
Thank you very much for your talk. It's great having you. Just this is a words of closing. Thanks for having been with us on site and online. The next talks are going to be next Monday. Be careful, it's at 6 p.m. because the speaker is coming in from Zoom. It's purely Zoom, so no room this time. It's Surya Ganguly from Stanford University. And the next Get to Know Your Neighbor is on 7th November, which will feature Professor Tanya Kaiser from Learn IC. And then don't forget, if you haven't yet signed up for the SV CIS retreat on October 13th, where our colleagues from SV are going to make open doors and show us the opportunities and challenges for AI in life sciences, please do so. Without further ado, have a nice afternoon and goodbye.